Hello and welcome to the channel. Myself Dr. Papu Dhibar, Assistant Professor in the Department of Chemistry, Brainware University. So today we are going to discuss about electronic spectroscopy. And this course is or this lecture is designed for the 4-year B.Tech degree course, and whatever their syllabus has, that has been covered here. Okay. So let's go into the topic. Spectroscopy. So what is spectroscopy? In simplest of terms, spectroscopy is simply the interaction between electromagnetic radiation or light with matter. So as we know it, that white light is made up of 7 different colors. Okay, so white light is made up 7 different colors. So if white light beams passes through a glass prism, it splits into 7 different colors, and this phenomenon was first explained by Sir Isaac Newton. So this is we have a natural example for this one, which is rainbow. So you can say that rainbow is a natural spectroscopy or an example of natural spectroscopy. So that is what it is. That is the interaction between the electromagnetic radiation or light with matter. So to understand spectroscopy, we'll have to understand electromagnetic radiation or light separately with matter. So first we'll go into electromagnetic radiation. So light is a form of electromagnetic radiation, and then this electromagnetic radiation actually travels in the forms of wave, that is light travels in the forms of wave, and this electromagnetic radiation or light has two different fields, that is one is electric field yellow in this case, and the other one is magnetic field blue. So you see these electric field and magnetic field, they are both perpendicular to each other, they are in the perpendicular plane, and these two planes are also perpendicular towards the with respect to the line of propagation of light. Line of propagation means the direction of the light with which the light is moving. Okay, so both the fields are perpendicular to each other, and the particles that are oscillating in those fields, either in electric field or in magnetic field, they are also perpendicular to the line of propagation of light. So that is what it is, and that is why it is called a electromagnetic wave, because of presence of electric and magnetic field. Okay, then we'll have to understand what is electromagnetic radiation. So electromagnetic radiation, as I said, is wave in nature. So if it is a wave in nature, we'll have to understand a wave. A wave is basically a sine curve where it looks like this. Also, it has maxima followed by a minima. The maxima are called crest, and the minima are called trough. So that it has some properties that we need to understand. So the properties of wave that we need to understand are: the distance between two crests or two trough is a wavelength. So that is a complete wave. Okay. Then we have frequency here. So the frequency is the number of complete waves per second. Number of complete waves per second is your frequency. And then the another important factor is wave number. Wave number means the number of complete waves per unit length. Unit length means it can be centimeter, it can be meter. So in 1 centimeter, how many waves, complete waves are present? In 1 meter, how many waves are present? So that is what is a wave. And also the energy of electromagnetic radiation or light is given by E is equal to h nu. So E is equal to h nu. E is the energy of light, h is the Planck's constant, and nu is the frequency of the light. So energy is directly proportional to the frequency of light, and every form of electromagnetic radiation has the velocity of speed or speed of light. So that is a constant, h is a constant, and as you can see, E is inversely proportional to the wavelength here. Lambda is your wavelength. So energy is directly proportional to the frequency, and the energy is inversely proportional to the wavelength. Okay. So now we have the electromagnetic spectrum. So this is the complete spectrum of electromagnetic radiation. only a small part of that is visible to human eye, but that is only a fraction of the electromagnetic radiation. So in this electromagnetic radiation, as you can see, as we go from left to right, the wavelength increases, and as I said that the wave energy of the light is inversely proportional to the wavelength. That means what? That means the energy from left to right is decreasing. So ultraviolet will have higher energy compared to visible, which again will have higher energy compared to infrared. It goes on like that. So next is the matter, that is our molecules. Matters are made up of molecules. So we'll have to understand how the matter or the light is interacting with matter, right? So how are they interacting? It is in terms of energy. We have seen that the light or electromagnetic radiation has energy. So has a molecule. So the total energy of a molecule is translational energy plus internal energy. Now the translational energy is a function of temperature, so it is not considered in spectroscopy. What are the internal energy? Internal energy are electronic energy, vibrational energy, rotational energy, and nuclear energy. So we are interested in this chapter about this one, that is electronic energy. So electronic energy corresponds to ultraviolet or visible range of the electromagnetic spectrum. Vibrational energy corresponds to our infrared region. Rotational energy corresponds to microwave region. It goes like that. Then if we see, the principal spectroscopy is basically this light, when they interact with matter, they either energy is absorbed, or then we measure that energy. If that is the case, that we are measuring the amount of light is being absorbed, then that spectroscopy is called absorption spectroscopy. Then another thing may happen, that is energy is absorbed, but when that energy, high energy state coming from the excited state to the ground state, it emits light. If that is the case and we are measuring that light, that is the emitted light, then it will be called as emission spectroscopy. Okay. So basically now we are going into the topic of electronic or UV visible spectroscopy. As you can see, electronic or UV visible spectroscopy, the electronic term comes from a molecule because of the presence of electronic levels in the molecules, or it is also called UV visible spectroscopy. Because why? Because the light or the electromagnetic radiation corresponds to this energy level. So the electronic levels present in molecules corresponds to ultraviolet visible region. That is why they can either be called electronic spectroscopy or UV visible spectroscopy. Now it is a type of absorption spectroscopy. That means we measure the absorbed light. So that serves. Now this absorption spectroscopy or UV visible spectrum or electronic spectrum serves almost as a fingerprint of a sample. Why? Because you see, the molecules have different or unique electronic structures, and because of that they absorb light, that is ultraviolet or visible light. They absorb light at a unique wavelength, and because the wavelength is unique, it is different for different compounds. So when a light interacts with, or rather a molecule interacts with ultraviolet or visible light, that is when the molecule absorbs the light of ultraviolet or visible light, then the electronic levels are excited. Electronic levels are excited means the electrons jumps from lower energy or ground energy level to excited state. That is what happens. So we measure that light. Okay. Now this is what an UV visible spectrum looks like. Okay, so we are giving some ultraviolet or visible light, sorry, and because of that, ultraviolet or visible light, because of that, that light is being absorbed by the molecule. And as I said, the light absorption occurs at a particular wavelength. So there is a particular wavelength where the substance or the molecule is absorbing maximum of the light. Then that wavelength, that particular wavelength, is called absorption maxima and represented as lambda max. Okay. Now, the base of this spectroscopy is Lambert-Beer's law or Beer-Lambert's law. So what happens? We have a light source. We are sending this light through a monochromator. Monochromator means at a particular wavelength, after passing through this monochromator, only one particular wavelength of light will come out of it, and then that light is considered as incident light. Incident light means the light that is entering our solution, that is the sample. In this box we have the sample solution. What is the sample solution? Here it is called a cuvette. Inside this we have the sample solution, and the incident light I naught is entering. After passing through that sample, what happens, some amount of energy, or sorry, some amount of light or radiation is absorbed, and the remaining light is the transmitted light. And if we consider the length of this cuvette is L and the concentration of our sample is C, then the absorbance is given by epsilon LC. Epsilon is molar absorptivity or extinction coefficient. L is the length of the cuvette or length of the solution, and C is the concentration of the solution. Then, so here you go, that is A is equal to epsilon Cl. A is the absorbance or optical density, C is the concentration of the solution, L is the path length. And as I said, epsilon is molar absorptivity and extinction coefficient. And IT, or transmitted light divided by incident light, is gives us transmittance. Okay. Now, so what happens is electronic transitions in molecules. So as I said, from molecular orbital theory, we know that certain molecular levels are present in molecules. What are those? This is sigma bonding, this is pi bonding, this is non-bonding, this is pi star or anti-bonding, pi anti-bonding, and this is sigma star or sigma anti-bonding. These are the molecular orbitals that are present in a molecule. And the possible transitions, what are the possible transitions? The possible transitions are sigma to sigma star, pi to pi star, and the other two are n to pi star and n to sigma star. So if we see the energy gaps between the molecular orbital levels, it is clear that the highest energy transition is sigma to sigma star, and the lowest energy transition is this one, n to pi star. However, if we consider symmetry, the symmetry allowed transitions are sigma to sigma star, or pi to pi star, and symmetry forbidden transitions are n to sigma star or n to pi star. Okay, so this can be determined by just understanding or knowing the value of epsilon. Epsilon value, or the molar extinction coefficient, if the value is greater than 10,000, then it is considered a symmetry allowed transition, which is the case for sigma to sigma star or pi to pi star transitions. And if the value is less than 100, then it is considered a symmetry forbidden transition. Now, what is a chromophore? Chromophore is simply a part of the molecule that gives its color by absorbing at a particular wavelength. Now, if we consider a benzene, it absorbs at a 210 nanometer wavelength. That is the lambda max. This is lambda max. That is the absorption maximum. That is, maximum of the light is absorbed at this wavelength. If we consider naphthalene, it absorbs at 220 nanometer. If we consider anthracene, 3 fused benzene rings, then it absorbs at 250 nanometer. It goes on like this. So the molecules that have a particular wavelength where it absorbs light, then that particular molecule or part of the molecule is called chromophores. Then next is oxochromes. What are oxochromes? Oxochromes are chemical functional group that when attached to a chromophore, that is the molecule that gives you an light, when it is attached with a chromophore, it alters or changes the wavelength or the absorption maxima of that molecule. Okay, so uh, the oxochrome, that is that functional group, or those functional groups are called oxochromes. And remember, the oxochromes usually themselves don't have color, so the color is coming from chromophore. But if we add oxochromes to the chromophore, it changes the or alters the sigma the lambda max value, that is the absorption maxima value, and also it may change the intensity of the color. Then we have bathochromic shift or red shift. So you see the absorption maximum, that is the lambda max, sometimes after treating something, some chemicals with some reagents, what happens, the absorption maximum may shift to a different wavelength. If it shifts to a longer wavelength means lower energy. So if it shifts to a longer wavelength, it is called mm, a bathochromic shift or a red shift. Okay, an example is phenol. When it is treated with dilute alkali, what happens, phenol is deprotonated and phenoxide anion is formed. So what happens here, phenol itself also has resonating structures, but because of the negative charge, after deprotonation, because of the negative charge, the resonance becomes stronger. So resonance becomes stronger. So what happens, because of greater resonance, the absorption maximum moves towards the right, that is towards longer wavelength. So a bathochromic shift or red shift is seen. We have hypsochromic shift or blue shift. It is exact opposite of red shift. What happens, when you treat some molecule with or a chromophore with a reagent, and the absorption maximum shifts towards the shorter wavelength or a higher energy, then it is called a blue shift or hypsochromic shift. So this happens when, an example of this is when aniline is treated with dilute acid. Dilute acid, what happens? Aniline has its own resonating form, resonating structures, as you can see here. But if we add dilute acid, what happens is this lone pair of electrons on nitrogen absorbs or attaches with the proton and becomes NH3 plus, and this extra NH2 group resonance is not present inside this benzene ring. So it cannot now donate, nitrogen cannot donate the electron pair now. So that is why the resonance is decreased, and that is why the absorption maxima shifts toward a shorter wavelength or a higher energy. Okay, so the point that I was discussing, that is the effect of conjugation on lambda max or the absorption maximum. As I already discussed, that as resonance increases, the absorption maxima goes towards a longer wavelength, and this is a vital example. As you can see here, we have only a one pi bond, that is ethylene. This molecule is ethylene. We have no resonance in here, only single pi bond is present. Here two conjugated pi bonds are present, so here it can go like this and do resonance. So from here to here, you see there is a greater resonance. As because the resonance is increasing, the pi to pi star absorption, as you can see, the lambda max of pi to pi star in this case was 174 nanometer. In this case, it increased to 217 nanometers. So the lambda max or the absorption maxima will go towards a higher wavelength if the resonance increases. If we increase a further pi bond, what happens? A further pi bond, you see, we have three conjugated pi bonds. So the resonance can go here, then go here, then go. So a longer resonance means again a smaller difference between the pi and pi star, and again the lambda max goes towards a red shift. Okay, and this can be exemplified from the nature itself. So as you can see, greater the number of conjugation, greater the amount of conjugation, greater the color. So the different types of berry colors, that is the violet color, it comes from anthocyanin that has a structure like this. So as you can see, there is a lot of resonating structure going on. Similarly, from carrot we get carotenoids. The carotenoids, as you can see, we have a very long chain of conjugated pi bonds, and that is why it gives you color. So the color comes from UV range to visible range, and as you know, visible range has lower energy compared to UV range, and that is why greater resonance means lower energy or higher wavelength. Same thing happens with saffron. Procetin also gives you greater resonance, so greater wavelength at lambda max. Okay. Steric can also have a factor in resonance. This is again the same example or the same explanation of resonance. But however, what happens here, in cis stilbene, two phenyl groups are in cis position. So because of that, because they are present in cis position, they are steric, they are facing a steric repulsion in here. So what happens, this benzene ring or this benzene ring goes out of plane with respect to this one, this double bond. So what happens if they go out of plane? If they go out of plane, the resonance cannot occur properly in these rings. So these resonance cannot completely and properly happen with this ring. So extended conjugation is stopped here. However, in trans stilbene, what happens, because they are in the opposite direction and far away from each other, there is no steric repulsion. So the resonance can occur, extended conjugation can easily occur in here. So that is why what happens is the lambda max of this one will be higher compared to the lambda max of this one. That is, the absorption maxima in cis stilbene will be lower compared to the absorption maxima in trans stilbene. Okay. And finally, one last example, that is the practical example. We have seen that we have used phenolphthalein as an indicator in acid-base titration. In acid, we know it is colorless. In base, we know it is pink. But in very high concentration of base, it again becomes colorless. Why is that happening? It is again, the reason again is resonance. Why? You see, there is a common resonance going on here, that is fine, but these cannot generate color. This happens below pH level of 8.2. Okay, so the any pH below 8.2, you will not get any color. But what happens between pH 10 to 13, because of deprotonation of these hydrogens, there is a extended conjugation, and this carbon oxygen bond here, right here, this bond is broken. So there is an extended conjugation with this ring or with this ring. So because of this extended conjugation, the lambda max shifts towards the visible range, and that is why we see the color pink. However, if the concentration of base is very high, then what happens? Then this OH minus, because of presence of higher concentration of OH minus, it attacks this center, and the resonance again goes back to O minus. So the resonance again limited to this center or this ring or this ring, and that is why no extended conjugation, and again the color is lost. Okay. So that is the all and